All right, so first and foremost, the one of two of the unit practice exercises worksheets are up and running. It's up on Canvas. You can do it at your leisure. We have a little bit of a PowerPoint to go over, and then we're going to start a lab, which is, I think, one of my favorite labs. Anytime we get to use Matchbox cards, it's one of my favorite labs. So, yeah, again, if you track that worksheet down, I believe it is due Friday. This unit is going to go through this week and then next week, and that will be it for Unit 1. So, let's go ahead and finish the PowerPoint. Linear motion and energy. Well, we talked a whole bunch about linear, but we haven't talked much about energy. No huge surprises about this one, but we should still talk about it. Okay, I think we did that. We did this, which leaves us here. Okay. So let's talk about energy. The fundamental thing you need to learn in physics about energy is there are tons of different types. We're going to start with the two types of energy that are most basic, and that is kinetic energy, the type of energy something has when it's moving, and potential energy, the type of energy something has when it has the potential to do something. You actually learned about kinetic energy in chemistry. That's the 1/2 mv squared. Molecules have kinetic energy, and we talk about two samples of gases at the same temperature have the same kinetic energy. So kinetic energy is the energy of motion, and its formula is 1/2 mv squared. So that's kinetic energy. And just like Dwight up there reminds you, energy is what we call a scalar value, meaning it cannot be negative and it does not have a direction. It has only a magnitude. There is no negative energy. Now the changes can be negative. You can have a change in energy that might be negative, but the energy itself will always be positive. So it doesn't matter if you're traveling with a velocity to the left or velocity to the right, velocity gets squared, so it doesn't matter if it has a positive velocity or a negative velocity, a squared velocity will always return a positive value. Hopefully that makes sense. You can't have a negative mass, so there's mass, it's always going to be positive, and velocity is going to be squared, so it doesn't matter if velocity is increasing or decreasing, positive, negative, it's always going to be a positive value. So kinetic energy will always be a positive value. It is a scalar. It also means it doesn't matter what direction it goes. We're going to talk very briefly in the next unit about vectors. Vectors have a magnitude and a direction. Talk very briefly about vectors, but they are not scalars. So values in physics are either vectors, they have a magnitude and a direction. You've talked about positive and negative, but directions can also be up, down, left, right, 20 degrees, 35 degrees. Scalars are always positive values. They just have magnitude. Okay. So potential energy is the energy of storage, basically the potential to do something. And we're going to focus right now on gravitational potential energy, but there's also chemical potential energy, elastic, nuclear, electromagnetic, and thermal that we'll all get into. We'll go over all these later on. Right now, what we care about is potential energy gravitational, or gravitational potential energy. So it's like this. Film canister, ball. If I drop the ball has the potential to do work or to do something to the film canister, right? Okay, pretty tough film canister. Anyway, you get the idea. So imagine there's a little spider right here. If I bring a ball up, it has the potential to squish the spider. So gravitational potential energy has the formula, the mass of the object, multiplied by the gravitational field it is in, and we'll learn more about gravitational fields in about a month and a half, times the height. Right now, gravitation is just going to be 10. We're on the Earth, we're on the planet Earth, gravitation's negative 9.81, we're just going to make it 10. Positive 10, because it's a field around the Earth. So if I raise this ball 1 meter over a surface, and let's say it has a mass of 1 kilogram, then 1 kilogram times 1 meter times a gravitational field of 10 gives you 10 joules. It has 10 joules of potential energy. Squish. And what that means is, as it falls, it picks up speed, losing height, therefore losing potential energy. But where does that potential energy go?
Into kinetic.
Into kinetic energy, exactly. So up here, before I drop it, it has a whole bunch of potential, but no motion. So it has a whole bunch of potential, but no kinetic. And as it falls, it loses potential because it loses height, but it gains velocity. It's a falling object. It's gaining velocity, so it is gaining kinetic energy. And this graph pretty well describes how it works. Why is it, why are these parabolas? See, like, so here, this ball has a whole bunch of potential energy. This is like a super ball that happens to bounce right back to its original value. Yeah.
Is that it? Is it because it starts from here, bounces, and then goes back up? Is that what
Yes, but why is it not just a circle? Why is it not like a half circle and a half circle? Why is it a parabola? So you have a whole bunch of potential energy. It loses potential energy, and while it's losing potential energy, it's gaining kinetic energy, and then it gains kinetic energy and vice versa. So why is it a parabola?
Acceleration rates?
Okay, you're getting there, but what does acceleration do?
Changes the velocity.
Changes the velocity. What do you know about velocity in the kinetic energy formula?
It's squared.
It's squared. And what do you need to make a parabola?
A square.
Something squared. So that's what's happening. So you're increasing your velocity, but you're increasing your kinetic energy by velocity squared. So that gives us a parabola kinetic energy, parabola potential energy. The sum of the two is the total energy, what we call total mechanical energy. Right now, two forms, kinetic and potential. Later on, more. Okay? Make sense? And we're going to be playing with this idea of energy pretty much the entire unit. This is, when it comes to physics, what does physics study? It studies matter and studies matter and energy. So this whole idea of increasing and decreasing energy will be a common theme throughout the whole year. Okay, so again, TME, total mechanical energy, is the sum of the kinetic energy and the potential energies. If there's only one object, there's usually just one of each. And systems of objects, we don't do until AP. So you won't have to worry about multiple objects all traveling together. We usually focus on one object. One object and its kinetic energy, one object and its potential energy. But I put the sum up there for anyone else who's using this PowerPoint out on the internet. Like, but you have to have the sum because there might be multiple objects. That's true. You have two train cars traveling together, they connect, all that stuff. So, but we're not going to worry about that. And then, so this is called the conversion of energy. Potential energy converts to kinetic energy, and cats.
That's a really good.
Cat tax.
I don't get it.
The cat goes from screaming to biting yellow and then the other one screams.
Yeah,
I understand.
that's the cat tax right there. When we, I think I'm going to skip over this for now. When we get to pendulums, we'll talk about potential and kinetic energy of pendulums. Hey, springs, again, this is potential energy. So this rock has potential energy, it can fall. Later on, we'll learn about elastic potential energy when you crush a spring. Fun stuff. And I think this is where we're ending. Okay, so simple exercises. This is where you take out a calculator and a pen or pencil and a piece of paper, and you work these through. A 350 kilogram ball is traveling at 68 meters per second. How much kinetic energy is it carrying? And I still haven't made my little icon, so I have a little icon where like, I'm ready, I'm working. I'm ready, I'm working. It'd be something cool. I didn't tell you, and I probably should have. The unit of energy is the joule, named after a guy named James Prescott Joule. It's given a capital letter J, because it's joule. James Prescott Joule did the pretty cool work of showing that all forms of energy are interchangeable, whether they be motion, kinetic, thermal, it's all interchangeable. So you got a 0.350 kilogram tennis ball traveling at 68 meters per second. How much kinetic energy is it carrying? How much energy will it impart to your face when it hits you in the face? I save this for you. Save this for my favorite classes. Anyone ever seen a Diet can popped from the inside?
Yeah.
You have? Like, I wonder how long it'll take to do this on YouTube. It's like, somebody's got to have done this on YouTube. It's like, it's crazy because I've done this probably with my class, probably about every year for like the last 12 or 13 years, and people are still like, I've never seen that before. I'm gonna pop the can from the inside out.
Okay.
Exactly. It's gonna be loud.
I'm open for it. Will it get on my computer though?
No.
Oh,
Alright, that is loud, huh?
awesome.
Anybody like warm diet cola? Yeah. Oh, really? Okay.
I'll try it.
Don't cut your mouth. A violin or a cello? Okay, so you pluck the guitar string, boom, it vibrates. You know what a guitar bow, you know what a violin bow does to a string? Something called slipstick resonance. And what happens is you have the bow, the violin bow or a cello bow or something, and it goes pop, 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 as it slides across. It's not actually sliding, it's kind of rubbing and rubbing and rubbing and rubbing. Kind of like if you take something really rough and rub it on your skin, it would like rub and pull and rub and pull and pull, like pull and release and pull and release.
Sandpaper.
Yeah, so it's called slipstick resonance. And that's what this does. You rub it on there, and it causes the aluminum to vibrate and vibrate and vibrate and vibrate and vibrate, it pops.
Where would you rub it? I want to scare my dad with it.
Me too.
I'll let you
Well,
investigate.
not a dad.
You rub it basically along the rim, like this, pushing down up a little bit.
Like on the rim or like on where you would open it?
Well, you rest it on the rim. So you push gently on the top, and you rest it on the rim. So it's like this is the rim with the valve withers. Eventually it goes vibrate, pow.
Awesome.
Great fun.
Alright, cool.
I saved that for you. I was going to throw it away, but I'm like, oh, I could do this for my physics kid. And they'll be like, get out of it. Because we will actually talk about resonance in about 5 months. So we'll refer back to it. All right. So if you got a value of energy larger than 100, raise your hand. Okay, keep it up. Larger than 200, larger than 300, larger than 400, larger than 500, larger than 600, larger than 700, larger than 800, larger than 900. Okay, what'd you get?
809.2 joules.
Yes, good. 809.2. So good. So 0.5 times 0.35 times 68 squared, 809 joules. Sound good, everybody?
Yes.
Okay. The thing you got to watch out. This is very important. Everything in physics uses standard units. So your mass, I gave you 0.350 kilograms intentionally instead of 350 grams. If you get a mass of 350 grams, make sure you convert that to kilograms. Everything in physics is standard units, and a kilogram is a standard unit. I know it doesn't sound like it should be, but it is. The kilogram is actually the standard unit. It's not the gram. The gram is simply too small. So everything is based on the kilogram. So mass, kilogram, velocity, meter per second, and so on. All right. Consider a 230 kilogram boulder that rests 45 meters above the ground. How much potential energy does it have? How much kinetic energy will it have if it falls the entire 45 meters? So go ahead and bang this one out. Bang it out. Take those computers and press some buttons and see if I give you an answer.
Potential
Pressing buttons, it's fun.
mass, gravity, height. 300 meters in the height.
about 500 pounds, by the way. If you're curious, if you ever looked it up. 2.2 pounds per kilogram.
Just put it in the formula. How much kinetic energy will I have? Velocity is 10 meters per second.
Okay, so do you have to do any calculations with for dot 2? Any calculations required for dot 2?
No.
No, because you realize, I mean, you can do all the kinematics equations if you want to, or you can realize that if it's 45 meters up, it has a whole bunch of potential energy. And that means right where it's the ground, all that potential energy has become kinetic energy. Make sense? So these two things should be exactly the same. Whatever potential energy it has at the top of the cliff is going to turn into kinetic energy right before it hits the ground. And if you got a number larger than 50,000, raise your hand. Larger than 70,000? Larger than 90,000? Larger than 100,000? Larger than 120,000? What'd you get?
103,500.
Yeah. About 103, 104,000? Give me a thumbs up if you're with me. Don't be afraid to ask questions. If you don't understand this, please ask questions.
The velocity is 10 meters.
All right, we're good to go.
And then the meters.
All right. I love this one. This is a test question too. A tourist drops her camera off the Hoover Dam. It took 6.1 seconds to smash into little pieces. How far did it fall? Now you actually have to do some kinematics exercises first, and then talk about how fast is it going, how much kinetic energy did it impart to the concrete.
Well, not concrete.
Impart to.
How fast is it moving when it died?
Mm-hmm. So it took 6.1 seconds to smash, and we're assuming she didn't throw her camera down. We're assuming she just dropped it. How far did it fall? How fast was it moving when it died? And how much kinetic energy did it impart to the concrete?
That's a very, alright. That camera is quite something.
It is.
Expensive camera.
Yeah, like,
How fortunate was I to find that picture?
Very fortunate.
this is insane.
I mean, someone probably just smashed it with a hammer, but
I don't think so.
precision.
Because like it's got like the lens is squished like oblong, like ooh, like a whole thing just went.
You are right, but it's on like a white background, so unless they grab every little piece.
Okay, great. I agree with you. Move on. Let's do the exercise.
It's 6.1 seconds. So it falls at a rate of 10 meters per second. How many meters per second? Yeah, 10 meters per second. It's still 10 meters per second. This is the velocity. Okay, so it falls for 6.1 seconds. And then the gravitational field is almost in seconds. That's velocity. Means that it fell for 6.1 seconds, which is 61 meters. Six point one seconds. 6.1 seconds. No, it's moving at a rate of 10 meters per second because of the gravity. Yes, you dropped it.
It accelerates at 10 meters per second per second.
Oh, wait.
Oh, cool. Chemistry will not mess up your equipment. You need it here for a couple days. Chemistry students have a tendency to play with physics students' equipment. Most of your stuff looks like toys. All right, what formula did you use to turn time into distance? What formula did you use to figure out how far it went in 6.1 seconds? Okay.
Distance is equal to 1/2 acceleration multiplied by time squared.
Yeah, excellent. D equals 1/2 AD squared. So we have something that is falling. So when we have something that is falling, we're going to use D equals 1/2 AT squared, and we might also use VIT plus 1/2 AT squared if something has an initial velocity, but it's just being dropped. We can basically, if it's just being dropped, this VI term disappears. So let me slow down. I think I went way too fast. If something is going to cover distance, it's going to cover a distance equal to VIT, that's velocity times time. So if it has an initial velocity, like you give it a push, that's VIT, plus 1/2 AT squared. It's right there, second one down. Okay. But in this case, you're just dropping it, so there is no VI, there is no initial velocity. So this term goes to 0, and you're left with D equals 1/2 AT squared. Does that look familiar?
Yes.
You handle this? Okay. So then we say, all right, well, 1/2, gravity is the acceleration, so 10, and it fell for 6.1 squared time. That's about just under 40, so just under 200. Is that about right?
Yeah, 186.05 meters.
186.05 meters?
Yes.
186 meters? Okay, so sometimes I go really fast, and I want to make sure I didn't just run anybody over. Okay? It's okay to ask questions. It's good to ask questions if you don't understand. If you do understand, give me a thumbs up. If you need me to go over it again, wave your hand around. Okay, so we have distance is going to be equal to velocity times time. Hey, don't shame him for asking questions.
No, I'm not saying that you should.
I don't know why you're.
I just need help.
I know, I'm just kidding. Okay, so distance is velocity times time. And so if something has an initial velocity, like you give the ball a push, it's going to cover a distance, velocity times time. Okay. And then acceleration will change velocity, and you can do a little math weighting and say, all right, if you have an acceleration, it's going to cover a distance equal to 1/2 AT squared. When you take calculus, you can figure out why this is the way it is. Right now, just memorize it. So since we don't have an initial velocity, this term disappears. And what we're left with is distance is 1/2 times acceleration times time squared. The acceleration is going to be -10. This could actually be -86. Does it say distance or how far? It just says how far, so we don't care about displacement. So 10 times 6.1 for the fall squared, 1/2 times 10 times 6.1 squared. So it fell 186 meters before it smashed into little pieces. And then what equation did you use for how fast was it going?
D is equal to velocity multiplied by time.
So the velocity is going to be traveling, it's going to travel 6.1 seconds. Gravity is going to be, does it say how fast? Yeah, we don't care about speed, we don't care about negatives. If it said velocity, we care about negatives, but it says how fast, all we care about is speed. So A is 10 and 6.1, so 61 meters per second.
Yes.
And then we use the 61 meters per second to figure out how much kinetic energy it imparted to the concrete. So that's just going to be How about green? So the kinetic energy, oh, let's get into green, equals 1/2 times whatever the mass was times 61 squared. Make sense?
Mhm.
Let's say it was a 1 kilogram camera, just put a 1 in there. 1/2 times 61 squared. 2 kilogram camera, 1/2 times 2 times 61 squared. Cool? And the energy was used to bust into little pieces. All right, so that is everything that is all I have to talk about for this unit. There's a bunch of other little bits and pieces that we will get together. I'll show some little demonstrations, but for the most part, what we're doing is just labs from here on out. And then in addition, that practice exercise. You have one practice worksheet this week and another one next week. Okay. So go ahead and grab the lab. It is velocity and energy with matchbox cars.
Velocity and kinetic energy with car load.
Yes. Car, C-A-R, not C-A-R-T.
Car.
I believe it's this one. Velocity, kinetic energy, potential energy with photo gates.
Oh, I accidentally downloaded it.
Good for you.
I apologize. I have a bad habit of naming things differently between Canvas and the actual lab document. Sorry about that.
It's okay.
I need an IEP for that.
I forgive you.
Okay. Our equipment is back here. Does everyone find the lab okay? Are you still opening it? Okay, I'll let you get some time to finish opening it before I yell at you. And as usual, put it in Google Docs so you can answer whenever possible. Hey, do me a favor. When you post like explanations, do them in different colors. It makes it a lot easier to grade if your font is a different color than my font. Sometimes hard to dig out some of the stuff you're doing.
Yes, sir.
Taking forever to download.
Yeah,
School Wi-Fi. Let's go.
Velocity with car. The other one's going to be with carts, plural, or carts with a T. Cars. We're just going to be cars. Okay. My chemistry class does not use the back tables. So you can actually use them. They're kind of dirty right now. Or you can use lab benches. They will be doing lab for a few days, so you're going to be okay. All right, so what you're going to do is you're going to get yourself a car, and you're rolling car down the track. Simple, right?
Yeah.
So, very simple.
Oh, yeah.
There's lots of cars to choose from. This is my personal favorite. It says free candy on the side.
Oh, no.
And there's more puppies in the van. What you're going to do is you're going to make a ramp system with as many books or as few books as you want. You're going to test 5 different settings. So you might do 3 books, 4 books, 5 books, 6 books, 7 books, and so on. And you're going to calculate how much, using the mass of the car, how much potential energy the car has before it gets going. Simple, right?
Yes.
What variables are you going to need to measure to figure out how much potential energy you have?
Height,
Height,
weight,
mass of the car,
and gravity.
and gravity is 10. Yeah, so height, mass of the car, and then 10. Okay? And then you're going to measure the velocity at the bottom of the track. What do you need to know for the velocity at the bottom of the track? or for the kinetic energy going at the bottom of the track. Yeah, to measure the kinetic energy at the bottom of the track, what do you need to know?
Acceleration.
No.
You're gonna need velocity. Now, it's gonna be really hard to find the velocity of this car because one, it's small, and two, these things are not known for their frictionlessness. So what we wanna know is what is the velocity right as it gets to the bottom? And for that, we're gonna use our old friend, for you, your new friend, the photo gate.
All right.
And what's gonna happen is you're going to set your photo gate, just like that. Feel free to tape it down because we'll be in this lab for 2 days, at least 2 days, and chemistry will not. So feel free to tape your stuff down and leave it when we're done today. Like put some tape down so it doesn't move because you don't want it to move. And what you're gonna do is you're gonna be like, boop, boop, and it's going to measure that blocked time as it goes through the laser. Make sense?
Yeah.
So that's gonna be pretty easy. The computer is going to know how long the beam is blocked. But it needs to be told what? In order to give you velocity, it's gonna know the time at which it was blocked, but you need to tell it what?
I don't know.
Boop, boop. Boop, boop. Well, if you're measuring velocity and you have time, then you also need boop, boop, distance, right? So you need to tell, if you weren't committed to it. You need to tell the computer how long your car is. Okay? You can be approximate if you want, there's rulers over there, but you basically just set it down and say, all right, from bumper to bumper, it's this long. Cool?
Okay.
These specific, and again, I don't care how long you make your ramp. I have found through experience that 2 lengths is about the minimum. Some of you are gonna be like, I'm gonna do 7. Okay, we got tons of lengths. But eventually you get to a point where it's so fast that these wheels just can't keep up and it tumbles. So that's probably your upper asymptote, the point at which the car falls apart and can't stay on the track anymore. But that's what you're doing. So there's some instructions on how to set it all up. Get yourself a laptop, and I will tell you right now ahead of time, at the end of the class, you will need to plug in your console, otherwise we'll run out of power, your LabQuest, and I recommend you plug your laptop in too. Okay? So get into your 4 groups, and hopefully, while you're doing that, I'm gonna install some LabQuest software on some more computers. So grab the 4 laptops, set up your station, choose a car, and then follow the instructions to set up the length of the thing.
I find these 2 tables.
Eddie, who, Aaron.
Well, that's momentum and collisions, and that's October. Yeah.
I want the freaking ID card. All right, we're done. Let's go. I have 2 cards in case you want to do one. We're going to have fun. My God.
I was basically appreciate to women.
Which means it limit. They killed their father. Yeah. If you need to know, the boss give us an operation.
Oh, yeah.
We do it. We make it super wrong.
Okay.
Internet.
Grab some soup if you want. No, I don't want to sue it. We made it wrong. So before we make this thing like 10 miles long, how long we can, how many books can we make it long?
That's a very good question. I have no clue.
This is weird.
Bro, all of these are dead.
No, they shouldn't be. I was like, no, it shouldn't be. It should have been charging over the weekend.
Hey, let's make this one.
Oh, so yeah. I'll go back.
This looks like a good time to me. Done. Take my long one. Let's try to make it jump.